same thing as saying let's get rid of the CO.
What?
In other words, wanting more hydrogen, steam injection, that's all good. But it's not like we're trying to get rid of the CO.
No.
No, okay.
No, CO is a wonderful fuel for engines. It's not a very good fuel for us. It takes the place of our hemoglobin and we suffocate. But in terms of combustion, it's a wonderful fuel. And that was another big aha here, was really realizing that carbon monoxide is combustible. It can take another oxygen, release energy. And its energy density by volume is about equal to hydrogen. Now by weight, we know hydrogen is the most energy dense fuel, but we're not, in a gaseous situation, we don't care about weight, we care about volume. So it's a bit of a red herring. But it wouldn't be for a plane. It'd be very relevant for a plane to be able to use hydrogen. But yes?
Are there any difficulties running the thing on aircraft altitude because oxygen content on the system?
It could be like a car. It's going to have less power because it's more diluted.
Okay, so you wouldn't take any
what?
adjustment? You wouldn't take any adjustments?
We're not doing mixture in this in the end. We're not trying to get to a complete combustion situation, so your dependencies there would be different than an engine. But last time I thought on my feet here, I forgot that there was nitrogen in gas. So I have to think about that for a second. Okay?
You got your memory right back here.
So, this is what I was going to show. So I just showed you the detail of the drying bucket, the pyrocoil. The drying bucket is done similarly. Here's the stages we went through on the auger drying bucket. We both have to get fuel in, and we want to feed that in at some motivated rate. It's interesting. Ideally, you'd like to separate the drying from the pyrolysis such that you can shut the machine down reasonably. So one of the problems in shutting these things down is you have a bunch of heat in the reactor, and if the fuel's sitting on top of it, it's going to continue to pyrolysize and dry. So like a wood stove, you'd ideally like to have an auger that you can shut off, and when you shut the thing down, it doesn't sit there and smoke. So the separation of the drying from the pyrolysis and having an auger feed between them has some advantages. If you can keep the pyrolysis separate from the drying, you can also keep the goo out of your drying and condensing system. Okay? Typically what happens in these monorator hoppers is the heat that's coming upward from the tar gases mixes with the water vapor, and so the condensate you get on the side is black goo. Okay? And then you open the top of it and it's completely covered in mess, and it's unfun. So if you can keep the drying, if you can input heat into your drying stage separate of the pyrolysis stage, then the inside of that condensing device will stay clean. You can open it, not have a lot of tar gas, and the condensate that comes out isn't completely polluted with nasty tars. So the toddy arrangement has a separate heat exchanger for the pyrolysis and drying. It would be possible to do that as a single heat exchanger, and previous systems like this have in fact combined them. Like the most important prior art to this is the Viking unit, which similarly tried to do a bunch of, this is at the Danish Technological Institute, similarly tried to do all of this pre-drying and pre-pyrolysis of fuel on the way in, but they mixed them. So you get a mixture of the pyrolysis and drying over this very long auger. Okay, they had a single auger that they did all of the heat exchange stages in. Okay, so one, it was very big. It's not terribly optimized for deployment, and two, the pyrolysis and drying are mixed. So if you're trying to run a condensing cycle, you're going to have a bunch of goo in your condensate, and secondly, it's difficult to start it up and shut it down because you have these zones mixed, and the heat will continue to pyrolysize your fuel. So we've separated those into two separate stages.
Are we going to talk about the deck configuration? If you know why you didn't build the deck in the same configuration, because in the deck you have also the pyrolysis and the drying all together.
No, they're separate. They're off to the side. But I mean, the current VEC does not have a dedicated drying stage, but it's the the bucket that's used underneath the hopper is a single wall vessel, but it's identical to the double walled one. So if someone wants to set up a drying stage on there, we haven't delivered it that way just because of the complexity of the unit. But if one wants to do the drying, pre-dry the fuel, you can change that bucket out to the heat exchange bucket. Okay? And it just replaces the current one that's on there. Now the problem is you don't have a really readily available source for the heat for that. You have a source, but it's too hot. So probably somewhere on the flue, you could take the hot gas off, maybe have an air mixture in it too to get it to the temperature you want, and then a fan that can take the temperature and you can run that through the bucket. So if you guys want to do that, we can do that. It's made anticipating that, but it was an elaboration that machine is so complicated. It does too many things. It does a lot of things, which I think is a feature, but it's overwhelming a lot of users to understand all of that. So there's a variety of elaborations on it that I haven't put on it yet, just to have it be tractable for folks.
Can you talk about rate control on the GAC and what happens if you're attaching it to a generator and the load increases so that the exhaust gas rates increase? And what
It's
happens?
fine. The exhaust gas, from quarter load to a full load, it doesn't really change enough to get us out of range. The engine can't really create too hot of gas for where I'm putting it. Okay, and the pyrocoil, when it goes down inside the reactor, it stops at a level that even at the lowest possible exhaust gas temperature that could be going through there, you wouldn't be pulling heat up out of the combustion zone. So we did a profile of what how pyrolysis sets up naturally, like what is the temperature differential, and the pyrocoil stops it at a point such that if the pyrocoil weren't operating at all, if the pyrocoil weren't operating at all, or at the lowest temperature that the exhaust gas could be, that would still be higher than what it would naturally be from the combustion zone. So you can't suck energy out of it. Okay.
So the engine demand still determines the rate of the GAC, the biomass.
Right. It's all a vacuum cooled system.
So as the engine demands more, creates more vacuum, and drives more combustion in the GAC.
Correct.
And then you don't run into a different regime as the rate goes up. And I'm wondering about heat transfer restrictions on the units. You find a good range to work in?
Yeah, and because the specific characterization of all those rates and capacities we don't know yet, but through direct experience, anecdotally, we know it works over the range we're interested in, but we don't have any numbers on it yet. But one of the pleasures of working in a combustion environment is that combustion and heat transfer, really combustion is so complicated and such a nonlinear phenomenon that it is only in the most recent time that we can model it in any reasonable way. But most all of the interesting things that have happened in combustion engineering historically were done with seated pants. Okay, and you can do a lot of things seated pants in it. There's a lot of refinements that the computational fluid dynamics is helpful for, but so much of this stuff, there's so many variables coming together. You just build it and test it. I mean, we can build, test, iterate faster than out of steel on our building system here, faster than models can typically happen. So we just build it and run the model as the unit and stick probes in it. Okay, so that's helpful for us because no one here can do CFD. So we just break stuff and rebuild it. Okay, so this is what the whole full toddy system looks like together, I'm not going to go through this right now, but if anyone's interested. So I've also, as I suggested in the beginning, there is a set of ideal thermal and chemical relationships here, and kind of formalized it out here. And this is what we're trying to progressively approximate with the GEC toddy. The ideal thermal relationships, I'll do this very fast. I've been told I'm late. The ideal thermal relationships are essentially what we had in the updraft unit. Combustion, all the heat from that goes to reduction. Everything wasted out of reduction goes to pyrolysis. Everything wasted out of pyrolysis goes to drying. Now, if you're doing that in a linear tube, you're getting all sorts of waste out the side. So the ideal situation to build a gasifier in thermally would be a series of concentric spheres. The combustion would be in the middle, and you couldn't waste any heat without it going through reduction. And then you couldn't waste any reduction heat until going to pyrolysis. Now, we can't realistically build a gasifier that's a series of concentric spheres. It's difficult to move fuel in that manner, so it violates the mechanical and gravimetric needs of a gasifier. But you can build them in a series of concentric vessels. So this is why you in general see the GEC is set up as a series of vessels within vessels. That's the best approximation. You lose stuff out the top and bottom, but all of your losses out of walls go into something that's useful. So you don't try to solve the problem by more insulation. You solve it by putting the zone that needs that heat next to the thing that's wasting heat. Okay? So, ideal thermal relationships, a series of concentric spheres. The problem is that looks nothing like what you want the chemistry to look like. Okay? The chemistry we went through we've so far gone through as the basic zones. We want them in the order of drying, pyrolysis, combustion, and reduction. The problem is that it's more complicated than that. We also need to distinguish between where we want the gases to go and where we want the solids to go. Remember, we're working with both solids and gases in this process. And the problem is the gases and the solids want to go to different places at different times if you're looking at what the raw chemistry you're trying to achieve. So, very quickly, if biomass comes in the system, it's dry. We get so the bottom here is the solid flow, the top is gas flow. In general, we're going left to right. So the output of drying is the water vapor and dry biomass. That solid dry biomass we want to take into pyrolysis, but the water vapor isn't helping us in pyrolysis, and in fact it's in the way. Okay? So we don't want to have it go here. We want it to skip. And in fact, we don't really want the water vapor in combustion either, because it's pulling down combustion. The next time, though we have to get it hot, but the next time the water vapor is relevant chemically is in reduction. So we really want it to skip those two steps and not go through them. The char we make in pyrolysis, we get two products, tar gas and char. The char, we don't want in combustion. We don't want to burn it there. We only want to reduce it. And in a downdraft, it's mixed. Okay, so we're burning some amount of the char off when we actually want to be saving 100% of it because we already don't have enough. Okay? So ideally, in the perfect gasifier chemically, we want the tar gas to go into combustion, be combined with air from some source, and burn, and not have any char that it can burn. And then have the char go around to reduction, and all of these things combine back together in reduction for the big finale, water vapor, heat, hydrogen, CO2, water vapor, and char, reduce it, and get to our output gases of H2 and CO. So that's the ideal gasifier chemically. Then you add on top of that the problem of mechanical fuel flow. It's very difficult to move solids. That interacts with gravimetric issues. That solids don't like to go up. They like to, at best, go sideways, and they really like to go down. Gases don't really care. Particularly when they're hot, they like to go up. So gases like to go in the opposite direction of the solids. In terms of redirects, when you're trying to do a heat exchange or transfer system, it's very difficult to redirect the solids. Solid material handling issues are difficult. Gas redirection is easy. You just do some plumbing. So the degree to which you're trying to establish heat transfer relationships, you typically want to do that by redirecting gases and not redirecting solids. Okay? So, the design of a gasifier in the end is this three-dimensional puzzle where you're trying to solve the thermal, chemical, mechanical fuel handling, and gravimetric realities of solids versus gases versus actually liquids in here, which I don't have, simultaneously. And all four of those problems have different solutions that don't like to play nice with each other. And thus the fun of biomass thermal conversion engineering begins. So that's the simple overview. It's all clear now? Absolutely.